In this video, we will be going over section 6.2. In this section, we are going to discuss another method to find the volumes of objects, which is called the shell method. Okay, volumes by shells. First, I want to go over this theorem 6.4, the volume of a shell. Okay, a shell with inner radius R1, outer radius R2, and the height h is said to have average radius R is equal to R1 plus R2 divided by 2. Okay, and the thickness is given by delta x is equal to R2 minus R1. Such a shell has volume V is equal to 2 pi RH delta x. Okay, if you have a shell with these properties, what are the properties? The radius of the inner cylinder is R1. This shell has the inner radius R1. This is R1. And the outer radius R2. This length is R2. Okay. And then we take the average radius. That means R1 plus R2 divided by 2 to be R. And then delta x is R2 minus R1. That is simply this length, right? The thickness of the shell. This is R1 minus R2 minus R1, right? Because this is R2, this is R1. R2 minus R1 is just the thickness of this shell. Okay, that is what we denote it by delta x. All right, then if that is the case, the volume of the shell is given by this formula 2 pi r h times delta x. Let's see if this formula is true. Okay, how do you find the volume of this shell? All I have to do is I have to find the volume of this bigger cylinder, and then I have to find the volume of this smaller cylinder, and then subtract the volume of the smaller cylinder from the volume of the bigger cylinder, right? Notice that this is an empty region. You remove this cylinder from the bigger cylinder to get the shell. Okay, when you remove this one, you get your shell. Okay, so let's find the volume of the shell and show that volume of the shell is equal to this quantity. The volume of the shell V is equal to pi R2 squared H. That is the volume of the bigger cylinder. Volume of this bigger cylinder is pi R2 squared H. You subtract the volume of the smaller cylinder, pi R1 squared H. Now let's simplify this and see whether we get this formula. Okay, so I'm going to pull out a pi times h because that's common for both terms. So you get R2 squared minus R1 squared. Now I can use the difference of square factors to factorize this. R2 minus R1, R2 plus R1. Now I'm going to do a small construction here. I'm going to put a 2 underneath here, and then I'm going to put a 2 to cancel that 2. Okay, so this 2 and this 2 will be cancelled. You get back what you had. Okay, now what is this? R2 minus R1. That is the thickness of your shell, right? That is delta x. That's the name that we gave. Delta x is the thickness of your shell. So I can replace this by delta x. And what is this? We took that to be R, the average radius. Okay, inner radius plus the outer radius divided by 2, which is what we call the average radius. And we denote it by R. So let's put that symbol there. 2 pi h delta x times R. Of course, you can rearrange this to write 2 pi r h delta x. So we have that formula. Okay. All right. So that's the volume of a shell. We'll be using this formula throughout this section. Let's move on. Next, I want to give you some sort of a motivation as to how we can use the shell method to find the volumes of objects. Okay, or if not, to approximate volumes of objects. Okay, our ultimate goal is to find the actual volume of objects, but let's try to approximate the volume of an object first using shell method. Okay, or in other words, using shells. Here is the example that I want to look at. Consider the solid obtained by rotating the region between f of x is equal to minus x squared minus x plus 8 and x-axis on the interval 0, 2 around y-axis. Approximate the volume of this region with 4 shells. Okay, we are asked to approximate the volume of this region with 4 shells. First of all, let's try to identify that object or that region that you obtain by rotating that given region. Okay, what region are they talking about? Region between this one, x-axis and y-axis, right? X-axis on the interval 0, 2 and y-axis. So if I graph this one, f of x, my function, you will get a shape like this on the interval 0, 2, by the way, because that's the interval that I'm interested in. Okay, this is the x interval 0, 2. If I graph my function, you will get a shape like this. Okay, now the region between the graph x-axis and the y-axis on that interval would be this region. This is the region that they are talking about. What you do is you rotate this region about y-axis. Then you get a shape like this, right? It's very clear that you get a shape like this if you rotate that about y-axis. Right? So now our goal is to approximate the volume of that object. The volume of the object that you obtain by rotating that region about y-axis. You need to approximate this volume. This is a 3D object. You need to approximate the volume of that object. Okay, so we are asked to approximate the volume using 4 shells. So what I'm going to do is I'm going to divide this interval 0, 2 into 4 subintervals. Okay, this is the first subinterval, second subinterval, third subinterval, fourth subinterval. Now, in each interval, I'm going to construct a shell. Okay, if I go to the first subinterval, what I'm going to do is I'm going to take the midpoint of that subinterval and I'm going to take the function height to be the height of the shell in that interval. Now, if I take, this is my function height. Now, if I take a rectangle like this, I can rotate this rectangle around y-axis to get a shell. Of course, if you rotate this rectangle around y-axis, you really get a cylinder, not a shell, because the inner radius is 0 in this case, right? Because this edge of the cylinder of this rectangle coincides with y-axis. If you rotate this rectangle about y-axis, you really get a cylinder, not a shell, okay? But what about the second rectangle? On this interval, I take the midpoint, I take the height of the rectangle to be the function height, and if I rotate this particular rectangle about the y-axis, this time you are going to get a shell, right? Because you have a positive inner radius in this case. Okay, your inner radius is this one and the outer radius is this one, right? All right, now likewise, in each interval, I take a rectangle and then I rotate that rectangle about the y-axis. That will give me a shell. Okay, that way I get 4 shells and the 4 shells are drawn here. As you can see, the sum of the volumes of those 4 shells is an approximation for the actual volume of the object, right? As you can see from this picture, all what you need to do is now you need to find the volumes, sum of volumes of these 4 shells. Of course, even though I'm saying 4 shells, this is not really a shell, okay? The other 3 are shells. This is not really a shell because it has a 0 inner radius. Okay, this is a solid cylinder. All right, so all what we need to do is to approximate the volume of this object. I have to find the volumes of sum of volumes of these 4 shells. So let's do that. I will call the volume of this inner one V1, that is the volume of this cylinder V1, and then volume of this shell, I'll call that V2. Okay, and then the next one V2, V3, and V4. This is V2, this is V3, the last shell is V4. Okay, so I need to find each one of them. How do I find V1? To find V1, I can still use this formula. Okay, I need to find the average radius R1 plus R2 divided by 2. R1 is the inner radius, R2 is the outer radius. If I consider this shell. What is the inner radius? As I said, it's not a shell, it's a cylinder. But what's the inner radius? Inner radius is 0. That's why it's a cylinder. It's not a shell. Okay. So inner radius is 0. You put 0 here. And then outer radius is this number. Okay. This is your outer radius. This value is 0.25. Pardon me, 0.5. This value is 0.5. So R2 is 0.5. So we can find the average radius. R is equal to 0 plus 0.5 divided by 2. And then what is the H for this shell? For this shell, how do you find the H? You take the midpoint and plug in that midpoint in your function to get the H. As you can see here, you take the midpoint and plug in that in your function. That is going to be, your H is going to be F of 0.25. Would you agree with me? Because this point is 0.25. From the scale, you can easily find it. That is your H. H is F of 0.25. Now I have everything I need to find my volume V1. Let's go ahead and find V1. V1 is equal to 2 pi R. R is the average radius. We found the average radius, which is 0.25 divided by 2. 0.25 divided by 2 times H. H is F of 0.25. F of 0.25. Okay. Now you can calculate this. This is just a number. You can plug in 0.25 in your function to find F of 0.25. That will give you the volume of the first shell. I'll call it a shell. Okay. Even though it's a cylinder, I'll call it a shell. Shell with a 0 inner radius. Okay. All right. V1 is, what is V1? If you calculate this, I'm going to write the value here. You will get 6.04. Okay. Similarly, you can find the volumes of the other shells. Okay. For example, to find V2, V1 is done. To find V2, we again need R, the average radius. Okay. Average radius is R1 plus R2 divided by 2. If you go to the second shell, this is the second shell. How do you find the average radius? Average radius is the inner radius plus outer radius divided by 2, right? Inner radius is this radius for that shell, for the second shell. The outer radius is this one. Okay. So that is, if you take the summation of R1 and R2, this is R1, this is R2, R1 and R2, that is exactly the midpoint of these 2 points, right? So if you take the midpoint of those 2 points, this point is 0.75. So you get R is equal to R1 plus R2 divided by 2. R1 is 0.5 plus R2 is 1 divided by 2, which is 0.75. Okay. What is H? To find H, you plug in this midpoint in your function. If you plug in the midpoint in your function, you get F of 0.75, right? This is F of 0.75. Okay. Now we are ready to find the volume of the second shell. V2 is equal to 2 pi times R. What is my R? R is going to be this quantity, right? I found R here, which is 0.75. 0.75 times H. H is F of 0.75. F of 0.75. Sorry, I'm running out of space there, but you can find this volume. Okay, you can find F of 0.75 by plugging 0.75 in your function. If you find this, you will get, you should get 15.76. That's the volume of the second shell. So on and so forth, you can find the volumes of the other 2 shells. I'm sorry, I'm forgetting the delta x here. Okay, you see in the formula 2 pi RH delta x. Here you have 2 pi RH. You need to have delta x here. What is delta x? Delta x is the length of a one subinterval. This is 0.5. Okay, so delta x is 0.5. You need to have 0.5 here. Here 0.5. Okay, and here also in the second case also you need to have a delta x. Delta x is constant, which is 0.5. Okay, and if you simplify this, you should get 15.76. Similarly, we can find the volumes of the other two shells. You will get V3 is equal to 20.37 and V4 is equal to 17.52. Okay. And the total volume, the approximation for the volume of the object that we obtain by rotating this region about the y-axis will be the sum of the volumes of these four shells. So the approximation will be V is equal to, I'll call this approximately equal sign. The volume of the object is approximately equal to V1 plus V2 plus V3 plus V4, which is 59.69 cubic units. Okay. All right. So that gives you an approximation for the volume of the object that we are interested in. Okay. You add the volumes of those four shells to approximate the volume of the object. All right. Let's move on. Next, I want to formally define the idea that we used in the previous example. Okay, so we need to find a way to find the exact volume of an object using that shell method. Okay, so let's go over this definition. Definition 6.5. Suppose S is a solid of revolution obtained by rotating a region on A, B around the vertical axis. If S can be represented with nested shells whose average radii and heights are given by continuous functions R of x and h of x on the interval A, B, then the volume of S is equal to this expression. Volume is defined by this expression. That is the limit as n goes to infinity, summation k goes from 1 to n, 2 pi r k, hk star delta x. That is by definition of definite integrals, that is going to equal to this definite integral. Okay, this expression is same as when you take the limit as n goes to infinity, this expression becomes this definite integral. In this definition, this rk is xk plus xk minus 1 divided by 2. Of course, this delta x, xk, they have the same meaning that we had in the Riemann sum section. Okay, delta x is always b minus a over n, xk is always a plus k times delta x. Of course, this xk star is a number between xk minus 1 and xk. Okay, and rk is the average of xk and xk minus 1. And hk star, this hk star is the height of the shell at x is equal to xk star. Okay, xk star is a number from this interval. Okay, what does this tell you? Rather than just pocketing this definition, try to understand, let's try to understand what this tells you. Okay, what this tells you is that first you divide. Suppose you are given a region like this. Okay, this is your interval and this is a curve. You are given a curve like this and you rotate this region about y-axis. Okay, about vertical axis, that is y-axis. If you rotate this region about y-axis, you are going to get a solid, right? You are going to get a solid, right? A solid like this. This is a solid. Now, to find the volume of this solid, that's the goal, right? We need to find the volume of this solid obtained by rotating this region about y-axis. Okay, to find the volume, I'm going to use shell method. Okay, first I'm going to divide this interval into n equal subintervals. n equal subintervals. Okay, let's say this is the kth subinterval. This is the kth subinterval, that is xk minus 1. This point is xk plus 1. Write it over here. This is xk. Okay. Now I'm going to construct a shell. So I'm going to take the midpoint and I'm going to take the height of the shell to be this height, this function height right here. And with that height, I can construct a rectangle here. Now, if I rotate this rectangle about y-axis, I get a shell, right? I get a shell. If I rotate that rectangle about y-axis, you will get a shell like this. Okay. Now, what I'm going to do is I'm going to find the volume of that shell. Okay. For each interval, you get a one shell, right? So let's try to find the volume of the shell that you get for this interval, kth interval. Okay. That volume is exactly 2 pi rk hk star delta x by previous definition. Okay. Rk is the average radius. Okay. Rk is this midpoint, that is average radius. That means xk minus 1 plus xk divided by 2. That is this one. And hk is the height of this cylinder at this midpoint. That's what we denote by hk star. Okay. Now this is simply the volume of the kth shell. But remember, I have n shells because I divided this original interval into n intervals. So I need to find the volumes of those n shells. I need to take the summation of this. I need to take the sum of this quantity as k goes from 1 to n. That will give the volume of those n shells. And the volume of those n shells would be an approximation for the actual volume obtained by rotating this region about y-axis, right? But now, if you want the exact volume, what do you have to do? As always, you take the limit as n goes to infinity. When you take the limit as n goes to infinity, your delta x becomes smaller and smaller. As a result, you get a better and better approximation. By definition of definite integral, this limit is nothing but 2 pi times the definite integral of this 2 pi times this particular definite integral by definition of definite integrals. Okay, that is the idea. Okay, all right. With that, let's move on. Okay, next I want to go over this particular example, which is the application of, which is an application of the definition that we discussed here, definition 6.5. Let's go over this. Find the exact volume, this time exact volume, okay? It's not an approximation. Exact volume means you need to calculate this definite integral. Find the exact volume of the solid obtained by rotating the region between the graph of f of x is equal to this function. This is the same function that we took in the previous example. Remember when we approximated the region, the volume of the region between this graph and x-axis on the interval 0, 2 around y-axis. Okay, again, the same example. This time they're asking us to calculate the exact volume. Okay, if I graph the function on that interval, you will get a shape like this. This is 2 on the interval 0, 2. Now what you do is you rotate this region about y-axis. Then you get a solid, right? You get a solid like this. This is a solid, okay? You need to understand that this is going to be solid at the end of the day. This is a solid. How do you find the volume of that solid? Well, thanks to this definition, we have a formula. The volume of the solid is given by 2 pi times the definite integral of this function, Rx, Hx. Can we identify our Rx and Hx in this case? Well, for that, we need to consider a shell, right? Let's say we have a shell with a very small thickness. This is your shell. It has a thickness, but I will use a single line, assuming that thickness is very small. Okay, this is your shell. For that shell, can you find Rx and Hx? See, this is along the x-axis, right? You measure the distance from the origin. So if I take this length be x, that is going to be my R, right? X is going to be the radius of that representative shell. This is my representative shell. Radius of that representative shell is going to be x itself if I take this to be x. Okay, so I'm going to take this general point to be x. Then I have my Rx. My Rx is x itself. And what is my Hx? Hx is the height of that representative cell. Height of that representative cell will be f of x, right? Because I just have to plug in this value in my function to find this height. So h of x is just f of x. F of x is, of course, minus x squared minus x plus 8. Okay. All right. Now we can go with the volume formula. We can find the volume of this solid object, this particular solid object, which you obtain by rotating this region about y-axis by using this formula. That is 2 pi times integration from a to b. Of course, your a is 0, clear. B is 2. Okay, integration from 0 to 2, Rx. Rx is this function. Hx is this function. Let's apply that formula. So the volume is given by exact volume. Okay, let me write it. Exact volume of the object is equal to 2 pi times integration 0 to 2 Rx, x times minus x squared minus x plus 8 dx. All what you need to do is compute this quantity. Okay, if you compute this quantity using a calculator, you will get 58.6431. What was the approximation in the previous example that we found? It was 59.69. It's not a bad approximation, right? The actual volume is about 58 something. The approximation was 59 something. As you can see, if you take smaller subintervals, you should get a better answer, better approximation. All right, let's move on to our next example. Here is the next example that I want to go over. Find the volume of the solid obtained by rotating the region bounded by the graph f of x is equal to 3 ln x, the line y is equal to, and the x-axis and y-axis around x-axis. You rotate that region around x-axis to get your object. Okay, let's try to first identify the region that they are talking about, the region that you want to rotate. Okay, to identify that region, I'm going to graph the given function. Okay, here is the given function. My given function is f of x is equal to 3 ln x. If you graph that, you will get a graph like this. Okay, this value is 1. You all know how to graph 3 times ln x. If you graph that, you will get a shape like this. And then, given this line y is equal to 2. Y is equal to 2. The line y is equal to 2 is this line. This is the line y is equal to 2. Okay, we are interested in the region bounded by this line, this function, x-axis and y-axis. That is this region. We are interested in that region. What you do is we rotate this region about x-axis. Notice that we need to rotate that region around x-axis. So if you rotate this region about x-axis, you will get an object like this. Okay, you will get an object like this. You basically rotate this region about x-axis, you will get a solid object like this. This is a solid object. Okay, all right. Even though it looks two-dimensional, it's a solid object that you obtain by rotating this one about x-axis. All right, how do we find the exact volume of this object. Again, can you use the shell method along the x-axis in this case? As you can see, along the x-axis, you cannot use the shell method because along the x-axis, you cannot construct any shell. You cannot construct any shells. But along the y-axis, you can clearly construct shells. For example, if you take a shell like this. So you have a nice shell there, right? Suppose that this shell has a width, but the width is very small. So that's why I'm using a single line to draw it, okay? So along the y-axis, you can place these nice shells. But along the x-axis, you cannot place shells, right? So that means this time to find the volume of this object, you need to use a y integration, not an x integration, because the base of a shell is located along the y-axis. Remember, we have to take this width of a thickness of the shell to be delta y this time, not delta x, because they are along the y-axis. Okay, so it is going to be an integration of y this time. How do we set up that integration? Okay, the key is always you take a representative shell. This is my representative shell. Notice that this shell has a width, okay? This has a thickness, but I draw a single line, assuming that my thickness is very, very small, okay? And here is my representative shell. Now I need to find the radius of that shell, okay? So to find the radius of that shell, so this is y-axis, right? You measure the distance along the y-axis from the origin. So if I take this to be y, this point to be y, the radius is going to be y, right? If I take this point to be y, a general point, that is going to be my radius, because that is the distance from origin to this point, which is y. Y is going to be my radius in that case. So radius is known. R of y, notice that this time radius is a function of y, okay? Not a function of x. That is y. Radius of the shell is simply y. And then what is the height of that shell? That is this length. I need to get this length in terms of y. Can I get that? Of course, yes, because I know this equation. This equation is y is equal to 3 ln x. From this one, I can find the inverse of this function to find this length in terms of y. Or in other words, this is the x value, right? This is the x value. This is the x value. You need to find this x value in terms of y. All what you need to do is you need to find the inverse of this function. Okay, so if you find the inverse of this function, you will see that we found the inverse of this function in the previous example actually. F inverse of y is going to be e to the power y over 3. If someone does not remember how to find the inverse, I will show the work here again one more time. You have the function y is equal to 3 ln x. I'm going to isolate my x. My x will be, of course, you need to divide both sides by 3 first. Then you have y over 3 in this side. In this side, you have just ln x. You get e to the power y over 3. Okay, so now that means your f inverse y is e to the power y over 3. That's how I found it. Okay. All right. Let me get rid of this. So that means I know this one. This length is nothing but e to the power y over 3. Okay. So I know the height. This is the height. Okay. So h of y is e to the power y over 3. Now I can go with my formula. I can find the volume using this integral. So now I need to figure out the integral bounds, lower bound and the upper bound. What is the lower bound? Lower bound is over here. Oh, pardon me. Lower bound is here. 0 to, this is the interval that we are interested in, because I'm rotating this region around y-axis, around x-axis. So this is the interval of integration. Okay, your y runs from here to here. That way you will accumulate all the shells. Okay, so integration from 0 to 2. So the volume is given by, exact volume of this solid is given by 2 pi times definite integral from 0 to 2 ry. Ry is y, hy is e to the power y over 3 dy. All what you need to do is you need to calculate this definite integral. Okay, if you calculate this, you will get approximately 24.48. This is the approximate volume. This is in cubic unit, by the way, cubic units. Okay, all right, that completes that example. Let's move on. All right, here is the next example that I want to go over. Consider the region bounded by the graph of f of x is equal to e to the power x and the lines y is equal to 0, y is equal to 3, x is equal to 0, and x is equal to 2. Use definite integrals to express the volumes of the following solids of revolution. The solid obtained by rotating the region around the x-axis. Do this problem in two ways. By integrating in the x direction and then by integrating in y direction. Okay, first of all, let's try to identify this solid that you obtain by rotating this given region about x-axis. Part A. The first thing I'm going to do is I'm going to identify this region. To identify that region, I'm going to graph this function first of all. So if I graph that function, you will get a graph like this. Okay, and then the line y is equal to 3. If you graph the line y is equal to 3, you will get a graph like this. This is the line y is equal to 3. And then the line x is equal to 2. I need to graph the line x is equal to 2. The line x is equal to 2 will be a line like this. This is 2, this is 3. And now we can identify the region. This is the graph of f of x is equal to e to the power x. This is the graph of y is equal to 3. And this is the graph of x is equal to 2. This is the x-axis and this is the y-axis. The region that they are talking about is this region in between those lines. Okay, so we identified the region. Let me maybe color that region. This is the region that we are interested in. Okay, in the first part, we are asked to rotate this region around x-axis. If you rotate this region around x-axis, you will get a picture like this. Okay, this is a solid. Okay, solid obtained by rotating this region about x-axis. This whole thing is a solid. Okay, now we need to find the volume of that solid. First of all, we can do one thing. We can find this breaking point. See, here we have a piecewise function, right? Up to this point, your function is e to the power x. Beyond that point, your function is y is equal to 3. So we can find this point. How do you find this point? You set these two functions equal. Y is equal to 3 equal to y is equal to e to the power x. So you have these two functions, y is equal to 3 and y is equal to e to the power x. You set these two functions equal to find this intersection point. So if you set them equal, e to the power 3, e to the power x, pardon me, you will get x is equal to ln 3. So this value is ln 3. All right, now we need to find this volume in two ways. Okay, first by integrating along x-axis, next by integrating along y-axis. How do you do? Let's integrate this along x-axis first. How do you find this exact volume of this object? By integrating along x-axis. To find the volume by integrating along x-axis, you can use the disk method, right? Because if you take a cross-section of this object like this, they are going to be disk, right? That cross-section is a disk. So we can use the disk method, right? So for the formula for the disk method is given here. V is equal to pi times a to b rx squared dx. But notice that you cannot have a single integration here, because here, see, this function is different from this function. So I'm going to split this integration into two pieces. One integration from here to here, and the next integration from here to here. That's what I'm going to do, okay? Because I don't have a single function. It's a piecewise function. So you have to do the integration for each of the piece. So how do you find the volume of this piece then? As I said, if you take a cross sections are disks. So you need to find the radius of the disk. Let's say this is x. At an arbitrary point, what is the radius? Radius is the height of this function. That is f of x or e to the power x. So I can use this formula to find the volume in that region. I'll write the total volume or just volume of the solid is equal to pi times integration from 0 to ln3. I'm going to integrate from here to here with this function, that is e to the power x. Rx squared, my Rx is, as you saw, that is e to the power x squared times dx. And then plus, I need to have the second integration from here to here. From here to here, your Rx is a constant. Your Rx is this height, which is 3, which is a constant. Okay, so that integration will be pi times ln3 to 2 squared dx. Pardon me, 3. This is radius is 3, not 2. This one is 3. 3 squared dx. Okay, all what you need to do is you need to calculate this integration. Okay, we are not asked to calculate it. So this is the setup of the integration to find the volume of this object. All right, that is along x direction. What about along y direction? How do you find? Perhaps let me put a small note here, x direction. This is integrating along x direction. And then integrating along y direction. How do you integrate along y direction to find the volume of the solid? Well, in the y direction, as you can see, you can use the shell method. Okay, in the y direction, you can take a nice shell. See, this is a representative shell. Again, you are going to have to consider two regions for this interval and for this interval separately. Okay, you need to use the shell method for this particular interval and this particular interval separately, because the height in this, when you are in this interval, the height of the cylinder is going to, height of the shell is going to be this much, which is a constant. But when you are in this region, height of the shell will be this height, right? If you take a representative shell, when you are in this region, your shell would look like this, right? So this height is the difference of this function and this function. Whatever the value here, and you find whatever the value here, you take the difference of those two values. All right, how do we set up this integral? First, let's focus on this interval. For that interval, we can use the shell method formula to find the volume. That will be, the volume will be, volume is equal to 2 pi times integration from 0 to, by the way, this value is 1, okay? This value is 1. 0 to 1. Ry times hy. What is my ry? Ry, the radius, if you take a representative shell in that region, radius is just y, right? If I take this length to be y, your radius is y. Okay, so ry is y, so you need to have y here. And then hy. What is my hy in that region? for that representative shell, what is hy? Hy is the height. Height is constant, which is 2. Okay, so we have 2. Hy is 2 here times dy. Okay, that's the first integral. That will give you the volume of this particular solid. That's not enough because we need to take this rotation as well. Okay, the volume that you obtain by rotating this region about the x-axis. All right, how do you find that using the shell method? Again, you take a representative shell like this. For that shell, again, the radius is y. If I take this general point to be y, your radius is y because radius is the distance from origin to that point. Radius is y, so ry is y. How do you find the height? To find the height, you need to find, let me actually draw that representative cylinder here. Here is your representative cylinder. Okay, so how do you find? I take this to be y, then the radius is y. To find this length or the height, you need to find this length first. How do you find that length? You can find that length by finding the inverse of this function. This is the function, graph of the function, y is equal to e to the power x. Y is equal to e to the power x. That means x is equal to ln y. Okay, so that means we found the inverse of this function. Inverse of this function is f inverse y is equal to ln y. That means this length is ln y. Now I can find this length, this height. That is 2 minus ln y because this whole thing is 2. This length will be 2 minus ln y, which is the height. So the second integral would be 2 pi times, this time integration from 1 to 3. Notice that I'm on this region now, 1 to 3. The radius, ry is y itself, times hy. Hy is 2 minus ln y dy. Okay, that is the integration along y-axis. That is the volume as an integration along y-axis. Okay. All right. Let's move on to the next part. All right. In the next part, we are asked to rotate the same region about y-axis, not about x-axis. X-axis this time. Okay. Then you will get a solid like this. This is the shape of the solid you get if you rotate this region about y-axis. Now again, you need to write that volume as an integration along x direction and as an integration of y direction. Let's deal with x direction first. To deal with x direction, we can use again shell method. Okay. For example, if you again you need to split the integration into 2 pieces. If you take a representative shell like this, when you are on this interval, you can integrate using shell method to find the volume of that particular object. Pardon me, when you are on this interval. Okay, when you are on this interval, you can find the volume of the object that you obtain by rotating this piece about y-axis using shell method. And then again, you use the shell method when you are on this interval to find the volume of the object that you obtain by rotating this piece about y-axis. That will give the whole object. Okay, if you take the sum of those two integrations, that will give you the sum of the volumes of those two objects, which is the volume of the desired object. Along x direction, I'll write x direction. The volume will be equal to, V is equal to, I'm using the shell method, 2 pi times 0 to ln 3. Notice that this value is ln 3. Okay, I'm first going to integrate on this interval. On that interval, my integration bounds would be 0 to ln3, and this is the representative shell. Okay, so then what is the radius? Radius is this length, right? That length is exactly x. If I take this general point to be x, radius is going to be x. So Rx is x. Rx is going to be x. So I should have x here. And then what is the h of x? I need h of x here. H of x is the height of this cylinder. Height of this cylinder is exactly this function height at this point, which is e to the power x, right? So you need to have e to the power x dx. And then I'm going to integrate on the next interval, remaining interval, that is ln3 to 2. ln3 to 2. What is the radius? If you take a representative shell in that region, that will be like this. What is the radius? Radius is again x, right? This length is, if I take this general point to be x, the radius is x. So R of x is x. What is the height? As long as you are on this region, the height is constant, which is 3. So you need to have 3 here, dx. That is the volume as a definite integral along x direction. Okay. How do you write the definite integral along y direction now for the volume? Well, for the y direction, we can use the disk method, because on this interval, if you take a cross section, the cross section is disk, right? This is a disk. And if you take a cross section in this region, in the second region, in this region, the cross section will be a washer. See, as you can see, you get a washer, right? You get a washer cross sections this time. So that means from here to here, I'm using the disk method to find this particular volume. And then from here to here to find the volume obtained by rotating this region about y-axis, I'm using the washer method because I have washer cross sections. Okay, so this will be equal to pi times first the disk method integration from 0 to 1. I'm going from here to here in y direction. The radius of the disk is 2. That's constant. If you take a cross section here, the radius of the disk is 2. I need to go with this formula. R of x is 2. So I have 2 squared dx. First integration. Second integration is pi times. This time I'm going from 1 to 3, but I have washers. Okay. So that means I'm going to have 2 squared. Remember, outer radius is squared minus the inner radius. Inner radius is ln y. Minus inner radius is squared times dy. Because this is the integration along y-axis, so you should have dy here. Okay. Oh, by the way, the outer radius, when you're on this region, if you take a washer like this, outer radius is clear. This is the outer radius, that is 2. How did you find the inner radius? This is the inner radius of the washer. Well, again, this function is known, that is y is equal to e to the power x. I found the inverse function to find this length. Okay, so you have y is equal to e to the power x. I need to find this length. That means I need to find the x value in terms of y, right? This is the x value. To find x value in terms of y, you need to isolate this x. That will be ln3. That's how I get ln, ln y. That's how I got ln y here. Okay. All right. That gives your volume as an integration along y direction. Okay. Yeah, that's the last example that I wanted to go over. With that, we conclude section 6.2. I'll stop there. I'll see you next time.